All right, we'll get started today, and I don't think I have any announcements. I think everything's pretty normal for the next week or so, but we will have, not too distant future, another exam review coming up, so I'll give you information about that. I'll just give a periodic reminder about course evaluations, which are open now, and you can do them online anytime, so please take the time to do that if you feel so inclined. So what we're going to start with today is our sort of usual Tuesday slide about stuff going on in the course related to grades and effort and performance and all that stuff. So you've probably, heard me too many times at this point stress the importance of doing all 4 homework attempts every week and how that's, at least at a basic level, the number one thing you should be doing to help yourself prepare for the exams in this course. So you might wonder, does this even matter, or am I just making stuff up? So I looked at some of the numbers related to this. So at the time that I tabulated these, there were 117 students in the course, so a few of you people have dropped, but so far most of you have stayed in. And if I look at how many students are following my advice and doing all 4 attempts every week, that's about 22. So right around 20%, a little bit less, are doing all 4 attempts every week. The rest of you have at least 1 week throughout the semester have not done that. I just sort of divided it up in the most crude way possible for this analysis. So people who have done all 4 attempts every single week, or those who at least one time have not. So of the 22 students who have done all 4 attempts a week, their exam average is 71%, which would put their current grade around a B- or B range, depending on what their exact homework scores and things are going on. So the students that are doing all 4 attempts a week are more or less averaging close to a B. And only 2 of those 22, 9.1%, are sort of in danger of failing the class with where they stand right now. And then for the students that have not done all 4 attempts every week, there's 95 of you. And the average exam score for those students is 60%, so 11% lower. And that would put their sort of course grade in the high C- to low C range. So there's quite a big difference, at least a letter grade different between the students who do all 4 attempts a week and those who don't. Again, these are averages, so results, of course, vary across a wide spectrum. But then 37% of those 95 students are sort of in danger of finishing below a C grade in the course. So then if if you know something about statistics, you might say, well, you can't just compare averages and say that they're significant, especially since the sample sizes are so much different. So I did a t-test on these results. Basically, I took every student's exam scores in the 2 groups and compare them via a t-test, and the p-value was 0.01, which is statistically significant. So of course there's a big spread within both of those. So I didn't quote standard deviations for these averages, but they're at least several percent in terms of deviation, but the results are significant when you compare the 2. So that does suggest, again, it's not necessarily a cause and effect relationship, but the students who are doing all 4 attempts every week are more often doing what is needed to keep up with the course than those who are not. So there's not a ton of time left in the class, but there is some time to change your habits, and we have a lot of practice homework assignments too that you can start doing if you feel like you've fallen behind and not done as much of this as you should. All right, so that's where we kind of stand right now in terms of that, and so that's something to think about, and I'll have to make sure I emphasize this more as we go towards the end of the semester. All right, so what we're moving into today is chapter 9, the last chapter in the course. It feels like we have a long time left in the semester, but there's actually only 3 weeks of class left for us because the semester ends on a Monday this year, so that last day is not going to be with us. So the plan is going to be these 2 weeks we're going to cover chapter 9. So Tuesday, Thursday this week, Tuesday, Thursday next week will be all chapter 9 material. And what you'll find about chapter 9 is it's a lot of topics, but none of them are covered in very much depth. So we expect you to know a little bit about a lot of things, but we don't expect you to know any of them in a great level of detail. And it'll be pretty clear what we expect you to know and what we kind of feel is beyond the scope. So we're going to spend 2 weeks on that, 4 lectures covering that material if everything goes as planned. And then the last week of the term that we'll meet here, we'll do parts of the final exam review. So the final exam review, as long as it is going to not be held in one marathon session, but we're going to do some of it in class, some of it at a separate session at the end of that week. So that's kind of what's coming. But today we're going to start chapter 9. So chapter 9 was reorganized in the new edition of the book, so this is the first time I've taught it in this order, so hopefully everything sounds coherent because I'm teaching it in different order than I did before. But basically what chapter 9 talks about are what are called condensed phases. So chapter 8 was all about gases. We talked at length about their properties and at the molecular level how they behave, and now we're going to do the same thing for the other 2 phases, which are liquids and gases. So we have to sort of start by let's contrasting the situations between what we had in Chapter 8 with ideal gases and now Chapter 9 where we're going to be mostly talking about liquids and solids. So one of the key assumptions of kinetic molecular theory, which we just covered last class, is that gas particles, again, be they atoms or molecules that make up a gas, they have no interactions with each other. So that's one of the key assumptions that's important to rationalize the behavior of gases, is that the atoms and molecules that make up those gases are not interacting with each other at all. The gas molecules are flying around and they're randomly colliding with each other, and they also collide with the walls of the container, which is why we feel pressure, but they don't have any attractions to each other. The gas molecules themselves are completely unaware of each other's existence. Now, what happens if we talk about real gases? So we talked at the very end last time, or towards the end last time, about real gases, situations where the behavior deviates from the ideal gas situation, and now what we're talking about in this chapter, which is liquids and solids. And the reality is that atoms and molecules are in constant contact with each other, so they do have interactions, and those are important then for determining the properties of these condensed phases and also for why real gases deviate from ideal behavior. Okay, so that assumption of kinetic molecular theory is not quite correct, and it's certainly not correct when we start talking about liquids and solids. And so what you have in these condensed phases, what we're going to talk about in this chapter, is a bunch of interacting forces. We're going to classify those forces a little bit starting today and sort of talk about how relatively strong or weak they are, but there's forces between molecules or atoms that hold them together. All right, because we introduced a little bit the difference between solid, liquid, and gas, and the difference is that in liquids and gases, the molecules are in constant contact. In liquids, they're rolling over each other, but they're always in contact with each other. In solids, they're sort of more fixed in place. And it's these forces between atoms and molecules that hold them together in liquids and solids, and that's going to be something that we will talk about today. So that's a key difference between gases, where those forces are non-existent in the ideal case, or very weak or very insignificant when we're talking about even real gases, versus liquids and solids where those forces are significant and they prevent the molecules or the atoms that make it up if it's an element, they prevent those particles from flying apart and going into the gas phase. They kind of hold them together in place, which is why they behave as a liquid or a solid. So that leads us to a more precise definition of what are called intermolecular forces. Now, if there's one thing you learn that sort of links a lot of different concepts in science, not just chemistry, it's the difference between intra and inter. So inter means between. We're talking about forces between two molecules or between two atoms in an elemental sample. So we're not talking about bonds in this case. We're not talking about chemical bonds that hold atoms together into a molecule. We're talking about forces of attraction between two molecules. And that's what inter means, is between. And it's a Latin prefix, I believe. Or more generally, between two particles. So they don't have to be molecules we're talking about. Again, if we have a atomic substance, an element that's just made up of atoms, there's going to be forces of attraction between the atoms as well. But we're not talking about chemical bonds that hold atoms together in a molecule. We're talking about forces between two molecules or between two atoms that are not bonded to each other. All right, so that's the difference between intra, which is the bonds, and inter, which are these weaker forces between them. So what we have to keep in mind then again is the distinction between intermolecular forces and some things that we've learned in the past. So remember, these intermolecular forces are not bonds between atoms. Those are a separate class. Those are called intramolecular forces, inter versus intra. You have to keep those straight. But we're not talking about bonds. We're talking about forces that exist between things that are not chemically bonded to each other, as I said. And also it doesn't, as a result, it's not related to covalent bond strength. So a lot of students get confused when they're trying to compare intermolecular forces. They think, oh, it's like the same as the covalent bond strength that we talked about in chapter, 2 or 3, where you have two atoms bonded together and we can predict which bond is stronger. We know how to do that now, but it has nothing to do with this when we're talking about intermolecular forces. It's a separate concept. So anytime we're talking about covalent bonds, those are what we call intramolecular forces. So again, intra means within. So those are forces that hold a single molecule together. Here we're talking about forces that hold groups of molecules together, okay? And they exist between the molecules. All right, so that's going to be sort of an important distinction to make, inter versus intramolecular. And as I said, as we go through today, we're going to talk about some of the types of intermolecular forces, which are important, especially when we talk about properties of liquids. These intermolecular forces also are important for solids, but they're kind of going to get their most relevance in our discussion of liquids today. And then before we go into more discussions on liquids today, let's talk about the different phase changes we would have. Because we are going to talk in some sense about how the intermolecular forces relate to these phase changes. That's converting a substance from one phase, solid, liquid, or gas, into another phase. And so let's talk about the terminology with those a little bit. We're going to define these more specifically later on, but we're going to use these terms, so let's just make sure we know a little bit about what they mean. So if we convert a liquid to a gas, that term we certainly have heard before, that's called boiling. So when we boil a liquid, we convert it from a liquid to the gas phase, or sometimes it's called vaporization. So those are more or less used interchangeably. Usually boiling is the process of heating a liquid until it goes to the gas phase, as we know from cooking, and then vaporization is sort of a process that would happen even at room temperature. We talked about vapor pressure last time a little bit. So vaporization and boiling are kind of mean the same thing, though. They mean converting a liquid to a gas. And then the opposite process, when a gas is converted into a liquid, is called condensation. All right, and we're going to give a more precise definition for this later, but at this point it's important to at least have a basic understanding of what boiling point is. So we should understand that if we're going to convert to a liquid to a gas, we have to add heat to it, because we need those molecules that are all sort of stuck together to be liberated from each other and off into the gas phase. You have to put heat into that for that to occur. So a boiling point is the temperature at which the liquid and the gas interconvert, at which a liquid becomes a gas, or vice versa, at which the gas becomes a liquid if you're cooling it down. As I said, we're going to get a more precise definition of this next time, I believe, next class, but that's for now what we just need to know about is the temperature at which that happens. And then the other phase change we're going to talk about, there's one other one that we'll get to later, but these are the two that we're going to deal with today, is converting a liquid to a solid. All right, so this we again have heard this term before. This is called freezing, when a liquid converts to a solid. And another term that you've certainly heard before is a solid converting to a liquid is melting. And so the freezing point, or it's also called the melting point, it's used both terms, but they're the same temperature for a substance. That's the temperature at which the liquid and solid interconvert. So if you have a solid and you heat it to the melting point, it would convert to a liquid. Or if you have a liquid and you cool it to that same temperature, it would convert back to a solid. All right. So freezing and melting, they're used interchangeably for that temperature. But again, in terms of what phase change they're describing, they are opposite of each other. But the temperature is the same. If you go to the freezing or melting point, the liquid and the solid will sort of both be existing in the process of converting from one to the other. And a key concept here, that the reason we're bringing this up now is because we're going to talk about intermolecular forces, and which we abbreviate as IMFs. And an important point in the relationship to these phase changes is that if you have stronger intermolecular forces, which we're going to abbreviate as IMFs, not International Monetary Fund, but intermolecular forces, that correlates with higher boiling and freezing points. Which hopefully makes intuitive sense. If we have stronger forces holding the atoms and molecules together in that liquid or solid, we have to put more heat into the system to be able to break those forces up and have the atoms start moving around more freely. Because if we're going from a solid to a liquid, that's what occurs. They're stuck in place in a solid and they start moving a little bit in the liquid. Or if they're in the liquid and they're moving around a little bit, but they're still kind of sort of in contact with each other, to get to the gas phase, we have to completely break them apart. And so if those forces are stronger holding them together, we have to put more heat in, which means the temperature that I have to go to is higher. Okay, so that's going to be the key relationship as we compare intermolecular forces, and then we'll relate them to these boiling and freezing points, and they are sort of directly related to each other. All right, so let's talk about the different types of intermolecular forces. Basically, we're going to give you really just 3 types that are important in this class. There's one other one that I'll briefly introduce just so you kind of know where it falls on the spectrum, but we're going to really just talk about 3 that we have to really worry about. And so the first of these is called London dispersion forces. I don't know why they're called London, to be honest, so don't ask. But anyway, it's a type of intermolecular force, and every element, every compound in the world has London dispersion forces between the atoms or molecules. So you're always going to have London dispersion force. Anything that has electrons, I should say. But of course, every real substance that we talk about does have at least 1 electron, so you're going to have London dispersion forces in everything. Now, what does it involve? So it involves what are called instantaneous dipoles. And this is kind of a little bit of a tough concept to wrap our heads around. I mean, the most important thing to know is that, again, everything has these types of forces, and as we'll get to in a little bit, these are the weakest type of intermolecular force that would be present in a substance. So that's the important part. Now, why do they happen is what's called instantaneous dipoles. What does that mean? So what we have is in nonpolar substances or in single atoms, we know that on average the electrons are distributed symmetrically around the nucleus or the nuclei if it's a molecule. So let's say we have 2 helium atoms. On average, the electron density is spherical. Remember, the electrons are in, for helium, 1s orbitals, as we talked about a long time ago. Those are spherical in shape, so the electron density is spherical in helium on average. So on average, there is no dipole. There wouldn't be any type of attraction between them. But what can happen is we know from the Schrodinger equation, from the idea of wave functions and all that stuff, that the electrons, they don't just exist in a sphere, right? There's a probability of electrons being at some place or the other that on average is a sphere, but at any given time, they're not necessarily going to be symmetrically distributed. So what happens with an instantaneous dipole is that at some period of time, again, because this is all probabilistic, you're going to have an unsymmetric distribution of electron density. Instantaneous, again, meaning that it occurs for just a short instant. It's not the average or the equilibrium type of place. So at some instant, you have an unequal distribution of electrons around the helium atom where you have a little bit of extra positive charge near the nucleus and a little bit of extra negative charge where the electrons are more localized. And then, think about static electricity that you've probably played with in physics classes or even in earlier science courses you took in school. If you take a balloon and you induce static electricity by rubbing it on your shirt, and then you hold it up to your hair gets drawn to the balloon. So basically what you're doing is you're then, in the same sense, in a sample of atoms, these instantaneous dipoles are inducing dipoles in other nearby atoms. So there's an unequal distribution of charge in this atom, and it's going to start pulling a little bit on the atom that's next to it, and it's going to induce an opposite distribution of charge in the other one. So you have these instantaneous dipoles, and then they induce dipoles in other atoms nearby, and you're going to have then a weak force of attraction between them because you're basically going to line up the opposite sides of the dipole in this way, kind of like static electricity pulls your hair if you have a charged balloon, just like if you have instantaneously charged atoms. Now again, these are instantaneous dipoles. They exist for brief instances. It's not like it's always like this, but at brief periods of time, you do have these forces of attraction. So on average, there is a weak attractive force between the atoms. And then this, again, is dynamic. It doesn't exist like this all times. So this distribution is then going to sort of fluctuate over time. We'll get the opposite distribution, but still an attraction. So again, these sort of electron density is sort of constantly fluctuating. It's not static, as we talked about in the wave function model, and that results in these weak attractions between them, where it's not a full positive or full negative charge, it's not a permanent dipole, but nonetheless it does result in some weak attractions between the atoms. And then the same thing happens in molecules. So let's say we have a nonpolar molecule like Br2. So again, on average, the electron density in Br2 is symmetric. It's not spherical in this shape because it's distributed over delocalized molecular orbitals over the whole atom, but it's still symmetric and nonpolar on average. But then again, because of what's called the polarization of the electron density, the ability of the electron cloud, if you will, to distort on brief instances of time, because it's not a static electron density, but rather a probabilistic model, you can get these distortions where the molecule is distorted in its electron density, where you might have a little bit more electron density on one side of the molecule than the other. And then that's going to line up with another molecule, which is going to induce a dipole that's opposite in direction, where you'll have the delta plus lining up with the delta minus over there, and so on. This is going to, again, fluctuate and go in all directions. But nonetheless, you have these instantaneous dipoles that lead to these weak attractions between molecules. So that's kind of why we have these London dispersion forces. Again, it's a little bit complicated to understand why that is, and we're not going to worry too much about that, but that's sort of the origin of this. It's this instantaneous dipole, or these brief distortions of electron density that then lead to these partial positive, partial negative charges attracting to each other. Now, as I said, the most important thing for this course is to understand, when are these forces stronger or weaker than others, and how do they affect the properties. So first, let's look at the boiling points of the noble gases. And we said just a little bit ago that the stronger the intramolecular forces, the higher the boiling point is going to be. So for noble gases, they're just single atoms flying around. They're obviously not polar because they're just single atoms. So the only type of force you're going to have in these are the London dispersion forces. All the other forces require polarity, which we don't have in noble gases or any nonpolar substance. So for noble gases, let's look at this. And so what we have is, if we look at the boiling points of the noble gases, helium boils at 4 Kelvin. So that means it only exists as a liquid from 0 to 4 Kelvin, very low temperature that it would boil at. And then as we go down the noble gas series, helium, neon, argon, krypton, xenon, and radon, we'll see that the boiling points gradually increase. So 27 Kelvin for neon, 87 Kelvin for argon, 121 Kelvin for krypton, 165 Kelvin for xenon, and 211 Kelvin for radon. Now, room temperature is roughly, 298 Kelvin. So all of these boil below room temperature, meaning they're all gases at room temperature, but they all have different boiling points, and they increase as we go to heavier and heavier noble gases. So the conclusion for this is that London dispersion forces are stronger when there are more electrons. As we go down the column of noble gases, we're increasing the number of electrons in the atom as we go down the column. And so we can see that the boiling point increases, which tells us that these London dispersion forces, the only type of intermolecular force we have, these are going to be stronger when there are more electrons. Or, as is often said, in heavier atoms or molecules, which again also means more electrons, but we say it that way also. Okay, so we have London dispersion forces being stronger when there are more electrons in an atom or molecule. And the reason for this is what's called polarizability. So polarizability is the ability of an electron cloud to distort. We said that these instantaneous dipoles require a distortion of the electron density. The electron cloud, as it's often called. All right, and so if something, so the greater it's able to distort, the more polarizable it is, and the more polarizable it is, the stronger these forces will be. And the reason why these heavier atoms are more polarizable, again, think back to things we learned back in chapters 2 and 3. The outer electrons are going to be, as you go down the column of the periodic table, like the noble gases, the outer electrons are going to be further and further away from the nucleus. So they're held less strongly by the nucleus, which means it's easier for them to distort. They take up a larger area in space, and they're not held as tightly, so they distort more easily. So outer electrons are held less tightly in the larger atoms, and that allows them to more readily distort, and that leads then to these stronger instantaneous dipoles, these stronger London dispersion forces. All right, pretty much everything
Or less after R, like R2 electrons are what?
held, H-E-L-D.
Yeah.
So they're held less tightly in larger atoms. And so that means heavier atoms are more polarizable because their electrons are further away, held less tightly, better able to distort. Pretty much everything in chemistry deals with the valence electrons, and this is no exception. Every chemical property, every physical property, a lot of that deals with the properties of the valence electrons, and this is no exception. The valence electrons are further away, they're better able to distort, and that leads to stronger London dispersion forces. And in situations where those are the only forces, that leads then to higher boiling point. Okay, so that's what we mean by polarizable, and that's how we sort of compare London dispersion forces. So as an example problem, let's rank the halogen molecules from lowest to highest melting point. All right, so the halogens X2, that's going to be the second to last column of the periodic table. They all exist diatomic in their natural states. So that's going to be F2, Cl2, Br2, I2. There's also acetine, but that one's radioactive, so we don't really talk about it too much because it's hard to study. But those are the main halogens, fluorine, chlorine, bromine, iodine. And again, as we said, in nonpolar molecules or atoms, so these are nonpolar because it's two atoms bonded together that they're same, London dispersion forces are the only intermolecular forces we have. So we have to remember those relationships. The stronger the intermolecular forces, the higher the melting point will be. We're here talking about melting point, not boiling point, but the same trend holds for boiling and melting. And in these nonpolar molecules, the only intermolecular forces we have are London forces. So we have some other types of intermolecular forces to introduce, but for nonpolar substances, London forces are the only ones, and they're going to be stronger in heavier atoms or molecules. So just like the noble gas series, the intermolecular forces are going to increase in strength as we go from the top of the column, which is fluorine, to the bottom, which is iodine, and then the melting points would then increase in the same way. So fluorine would have the lowest melting point in this series, Cl2, and then Br2, and then I2. So that's the ranking of those, again, just going from lightest to heaviest when we're talking about intermolecular forces or any properties related to those. And if you remember the standard states of these elements, that might start to make sense now. So F2 and Cl2 are both gases at room temperature in normal conditions. That means they have relatively weak intermolecular forces. Br2 is a liquid. It has stronger intermolecular forces, so at room temperature it's able to exist as a liquid. And then I2 is a solid. So again, that also makes sense based on their intermolecular forces. So again, these two are gas, Br2 is a liquid, and I2 is a solid at room temperature at normal conditions. And that again is because of the increasing strength of the intermolecular forces as you go from F2 to I2. The strongest intermolecular forces hold the molecules together more tightly, and that results in it being a solid at room temperature versus the other ones, okay? So any questions on London dispersion forces for now? All right, the next type we're going to introduce are called dipole-dipole forces. And we're kind of, London dispersion forces are exceptionally weak. Now we're talking about forces that are a little bit stronger, but these are still a lot weaker than chemical bonds. These are about 1% as strong as chemical bonds. So chemical bonds that hold atoms together in a molecule are much stronger than the intermolecular forces, but for dipole-dipole forces, they're around 1% the strength of a chemical bond. Of course, that varies from substance to substance, but that's nonetheless going to be what we have. And so which molecules have dipole-dipole forces? Well, as the name suggests, it's any molecule that has a dipole. So that's going to be any polar substance. So we're talking about, for dipole-dipole forces, any polar covalent substance. And again, this is also key, is that we must be talking about molecules that are polar overall, not just molecules that have polar bonds. So in chapter 4, we talked about how to predict the polarity of a molecule being polar or nonpolar. So it has to be a substance that is overall polar, not just something that has polar bonds. So any molecule that we would predict to be polar using arguments that we learned back in chapters 3 and 4, any polar molecule is going to have dipole-dipole forces. Those are going to be stronger than the London dispersion forces. The London dispersion forces still exist, but these dipole-dipole forces are stronger. And typically the properties of a substance are going to be dominated by whatever the strongest intermolecular force is. So for polar substances, the dipole-dipole forces are more important than London dispersion because they're the stronger forces holding them together. But it's not that the London dispersion forces cease to exist. So these are a little bit more straightforward to understand. So if we have HCl, a very simple polar molecule, as we learned back in chapters 3 and 4, you'd have a delta plus on the more electropositive atom, which is hydrogen, a delta minus on chlorine, meaning there's a net distribution or net unequal distribution of electron density in this molecule. And then these will line up with other molecules that have the opposite polarity. So you'll form these sort of networks where a delta minus from another molecule and delta plus line up in an opposite sense. So you get attractive forces. So we're going to show attractive forces in blue, and then we'll show repulsive interactions in a different color. So in red, I guess I'll do repulsions. So when you have these sort of dipole-dipole forces, you can have both attractive and repulsive interactions. Attractions when you have the opposite sides lining up, but then between the ones that are the same, you would also have some repulsions as well. So both happen, but it's sort of a balancing effect, and the molecules are typically going to line themselves up in a way that the attractive forces are maximized and the repulsive forces are minimized. So in net, you're still going to have an attraction between the molecules as a result of these dipole-dipole forces. So then what you'd have is you can have larger networks than this. So this is going to line up with another HCl where you have a delta plus, delta minus there. That's going to give you an attractive force, and then you're going to have delta minus and delta plus lining up there for an attractive interaction, attractions there, and again you're going to possibly have repulsive interactions between the ones that have the same partial charge, like 2 chlorines or 2 hydrogens, but nonetheless those are further apart, and so in net the attractions are stronger and the molecules are held together by these dipole-dipole forces. All right, so it's a net attraction between them. Okay? Yeah? You have a question? All right, so, okay, so then, so there's, attractions and repulsions, but the attractions sort of win out. The molecules are going to line up in a way that the attractions are stronger than the repulsions. That's how molecules typically arrange themselves, and that's what we end up with, okay? So that's dipole-dipole forces. And then there's one other type, which is, it's given a separate name, and so we're going to, expect you to be able to distinguish dipole-dipole forces from hydrogen bonds. But hydrogen bonds is just a special type of dipole-dipole force, but it's a particularly strong one, so that's why we talk about it sort of in separate terms. And any of you who have taken biology class, or you certainly will learn about this in biochemistry if you haven't seen it in that class, hydrogen bonding is very important in biological context as well. And these can be around 5 to 10% as strong as chemical bonds. So we said dipole-dipole forces typically are on the order of 1% as strong as a bond. These can be 5 to 10%, so they're much stronger than a typical dipole-dipole force. And so it is a dipole-dipole force. It's nothing really different, but it's just a special type. And so that's why we classify it separately. They're particularly strong dipole-dipole interactions in certain compounds. Not everything has these, of course. Now, as the name implies, hydrogen bonds involve compounds that have hydrogen in them. So these are particularly strong dipole-dipole interactions in certain compounds, and they are compounds that have hydrogen. That's what the name sort of tells us. And so molecules that are going to have hydrogen bonding interactions are ones that have very polar bonds to hydrogen. So if they have HF bonds, which really the only substance that has HF bonds is HF itself, fluorine is very electronegative, so the bond between hydrogen and fluorine is very polar, and so those would have hydrogen bonds. And then if they have OH bonds, oxygen is the next most electronegative element. And so you get very polar bonds. This would be something like water or alcohols or carboxylic acids that we talked about, like acetic acid. Or the last type would be ones that have NH bonds, where again you have partial positive on hydrogen, partial negative on the element it's bonded to. And so molecules that have one or more of these bonds, HF, HO, or HN, will be ones that would exhibit hydrogen bonding. So the reason that this is particularly strong is for two reasons. One is that these are very polar. So these are very electronegative elements. And so the bond between those elements and hydrogen is very polar, so it's a stronger interaction because of the higher polarity. But also remember that hydrogen is very small. So when you have these types of bonds that involve hydrogen, the molecules can pack really close together because the hydrogen atoms are small. And so that ability for them to get really close to each other also makes the interaction stronger. So both the polarity and the ability for them to pack really close together because of hydrogen's small size makes these interactions very strong. So examples of molecules that would have hydrogen bonding interactions are some very common substances. HF itself, which is really the only molecule that has bonds between hydrogen and fluorine. Water, the hydrogen bonding in water is exceptionally important in a lot of contexts. Or CH3OH, this one only has one OH bond instead of two, so it would have weaker hydrogen bonding, but it would still be there. Or ammonia, NH3, which has NH bonds. So basically any substance that has bonds between these elements and hydrogen would exhibit hydrogen bonding. All right, so that's a specific type of dipole-dipole force, significantly stronger, but only occurs in these select scenarios. Now the last one I'm going to talk about, which I don't think is going to really be something that you're going to be examined on in this course, but just for completion, I wanted to sort of introduce it. You'll come back to these ones a little bit more detail in, I believe Chem 2 kind of covers some of these more specifically, so I'm just going to briefly introduce them here just for completeness, but again, I think we're going to 99% of our focus is going to be on the previous three that I talked about. So if we have ionic compounds, there are also intermolecular forces involving them. So we're going to talk about the structures of ionic compounds at the end of this unit, so it's going to be a while before we get all the details. But when you have ions in an ionic compound, forces between the opposite ions hold them together. We called that ionic bonding earlier. And so these ion-ion forces are kind of a gray area between, a chemical bond or an intermolecular forces. But in ionic crystals, you have these interactions in all directions. They're not just sort of, directional localized bonds between two ions. They're kind of these sort of charge interactions going all directions. So it's kind of a gray area between, inter and intramolecular. But these ion-ion forces are very strong. But we classify them more as a bond than an intermolecular force. But they're kind of, again, in this sort of continuum. So when two ions that interact, there you have sort of permanent charges like sodium and chloride, and you're going to have these strong interactions because of the opposite charges. And as we'll learn at the end, these interactions go in all directions. It's not just two ions interacting with each other in sodium chloride, they're all interacting with each other in 3 dimensions. And those are probably better classified as ionic bonds than as intermolecular forces, but they kind of fall into that similar category. And then another one that you'll talk about in Chem 2. So in this course, Chapter 9, we're only dealing with pure substances. So that's why this last one here is not going to be one that we're going to actually talk about any more than this. So in pure substances, you don't have these, because in pure substances, you just have one type of substance, which means that you're going to be, just determining whatever intermolecular forces that single substance has. In Chem 2, you're going to start talking about mixtures of two substances, and then how does that change the intermolecular forces when two things are mixed together. So when you make an aqueous solution, which we did talk about here in this course in Chapter 6, you can have interactions between the ions that are dissolved and the dipoles of the solvent that they're dissolved in. So when you have polar molecules dissolving ionic compound, you get these ion-dipole forces. Again, these are only going to be found in mixtures, in solutions of ionic compounds. And so our, Chapter 9 doesn't talk about those anymore, so I'm not going to go any further than this. But in case you're just wondering how that works, based on our discussions in Chapter 6, when you dissolve an ionic compound in water, you have interactions between polar molecules and ions. And again, those are most prominent in aqueous solutions. So this, on some level, would be an intermolecular force as well, because if you have, for example, the polar water molecule, if we dissolve sodium chloride in water, we're going to get sodium ions, which are positive, chloride ions, which are negative. And so this polar water molecule, which has partial positive and partial negative charges, is going to be attracted to the positive sodium ions in that way. Or if you have the chloride ions, they're going to be attracted to the partially positive hydrogen atoms. You get these types of interactions between the opposite charges. So those are called ion-dipole forces because they involve an ion and a molecule of the dipole, but those only occur in solutions. That's the last we're going to see them for this chapter, because this chapter only talks about pure substances, things that are not mixed together in two or more components. All right, so that's going to take us then to a final summary, which is, the different types of intermolecular forces we would have. And really, as I said, there's three that we need to worry about. So dispersion is the weakest. Dipole-dipole in the middle. And then hydrogen bonding being the strongest. All right, so when we're doing problems like this, where we have to sort of categorize and make predictions about the types of intermolecular forces we have, this is the order they come in, weakest to strongest. Ion-dipole is even stronger than hydrogen bond, but we're not going to talk about that, as I said, because it's only found in mixtures. So these are the three you need to worry about. And as I said, the properties of molecules are going to be dominated by whatever the strongest force is. So when you're classifying molecules and trying to figure out, what's the relative boiling point of these substances or melting point or whatever property you're trying to compare that relates to these intermolecular forces, you need to be able to identify especially what the strongest intermolecular force is, because that's going to be the key determinant of the properties, especially when comparing one substance to another. All right, so that's how we have to sort of think about them in terms of their relative strength from weakest to strongest. And so that leads us then to problems like this, where we're going to be able to compare two different substances which might have two different types of intermolecular forces, and then decide something about their relative properties, in this case, boiling point. So if we have CO2 and COS, carbon dioxide and carbon oxygen sulfide, which one is going to have the higher boiling point? So to do this, we need to be able to, think about the geometry of the molecule. So the first thing is to predict whether it's polar or nonpolar, and then of course whether it has bonds between hydrogen and an electronegative element. These don't have hydrogen in the formula, so they can't have hydrogen bonding, so we can rule that one out. But for each of these, we need to decide what is the strongest intermolecular force. Is it London dispersion forces, which would be true if it's nonpolar, or is it a dipole-dipole force, which would be true if it's polar? So for both of these, we need to predict whether it's polar or nonpolar. So we talked about CO2 as one of the first examples of a molecule that has polar bonds. So you have polar bonds between carbon and hydrogen, but they cancel each other out. So again, in linear molecules like this, where you have two identical atoms bonded to the central atom, this is a nonpolar substance, AX2, if we want to go back to the classification we learned in chapter 4. So this chapter does require us to remember some things, especially from chapters 3 and 4. And the key concept for predicting intermolecular forces is polarity. So we have to know that this is a nonpolar molecule, and if it's nonpolar, that means it has London dispersion forces only. All right, so anything that's nonpolar, that's the only intermolecular force. And then if we go to the other one, which is COS, COS has an almost identical structure, but this time instead of two oxygens, we have one oxygen and one sulfur. And so what we have in this molecule is carbon-sulfur bonds are pretty much nonpolar. I think there's like a little bit of a dipole towards sulfur, but it's very tiny. And we still have this dipole towards oxygen. But because we don't have two of the same atoms bonded to carbon, the dipoles don't cancel each other out anymore. So we have a net dipole in this molecule towards oxygen. All right, with two different atoms bonded to carbon, the polarities don't cancel out because they're not the same dipole. And so we have a net dipole in this molecule, and it turns out it points towards oxygen. So because there's a net dipole, this is a polar molecule. And because it's a polar molecule, the strongest intermolecular force it's going to have is not London dispersion forces, but it's going to have those dipole-dipole forces. All right, so dipole-dipole forces are stronger than London dispersion forces. The stronger intermolecular forces leads to the higher boiling point. So this is going to be the substance that we would predict has the higher boiling point, and I believe, and I'm 99% sure that's true. So based on the predicted intermolecular forces, this one should have a higher boiling point. We know that CO2 is a gas at room temperature. I don't know off the top of my head what COS exists at, but it would be a substance that is boiling at a higher temperature than carbon dioxide. Okay, so that's going to be how we make predictions about molecules based on their intermolecular forces. And again, you need to focus on the strongest intermolecular force. Now, if they both have the same strongest intermolecular force, then you have to break it down a little bit further and figure out, okay, well, which of those is stronger in an absolute sense between the two. But for this one, there's two different types of forces, and clearly the dipole-dipole forces are the stronger ones. Okay, so any questions on that so far? All right, so what we're going to move on to next are some other properties of liquids, which also are related to and depend on the intermolecular forces. So there's going to be four types of properties we're going to talk about. So the first one is surface tension, and surface tension is the resistance of a liquid to increase its surface area. Now that's kind of a technical definition of surface tension, but we've all experienced surface tension. If you've seen, a drop of water sitting on a leaf or a blade of grass, why doesn't that water drop just like spread out? Well, it's because of the surface tension in the drop that sort of holds it together. It prevents the drop from spreading out and increasing its area. So surface tension is, and all of these are related to intermolecular forces. So surface tension occurs because at the surface of a liquid, in net, you have intermolecular forces sort of pulling the surface inward, because the intermolecular forces exist in all directions, but at the surface, you don't have any more molecules above it, so in net, the intermolecular forces are pulling downward on the surface, which sort of holds it together into a droplet. And so it's at that surface where you see that. And the other three of these properties are kind of all related to surface tension as well. So surface tension is one of them, and again, the stronger the intermolecular forces, the higher the surface tension. So water as a liquid has relatively strong intermolecular forces. That's why it forms those nice, often spherical droplets that we see on a rainy day. And then the other three are again related to intermolecular forces and kind of along the same lines. And so the first one is capillary action, or if you're from the UK, capillary action. And it's the spontaneous rising of a liquid through a glass tube. It doesn't necessarily have to be glass, but that's kind of how it's sort of thought about. So if you take a very thin glass tube and you put it into water, the liquid will start climbing up that tube naturally. And it's not that it's not opposing gravity, but it's basically that you have intermolecular forces both in the liquid itself and forces between the liquid and the glass surface that it's in contact with, and that's kind of, again, pulling the whole thing in that one direction as a result of those intermolecular forces. So that's capillary action. And then capillary action is also related to what are called adhesive and cohesive forces. So adhesive forces are forces of attraction between a liquid and the container. So when you put a liquid in a container, the surface of the liquid and the surface of the container that it's in are going to have some sort of interactions between each other. And these types of properties, these types of phenomena, surface tension, capillary action, all that is usually done in glass containers. That's where we usually study things. So it's important to realize that glass is polar. We're not going to talk about the structure of glass in this class. It's actually kind of complicated, but glass has a bunch of OH groups on the surface. So with OH groups, you have polarity and hydrogen bonding and all that stuff. So you have polar things on the glass, polar groups in the water, especially if it's a water to liquid, and so those kind of interact with each other via dipole-dipole or hydrogen bonding type forces. So those are called adhesive forces when it's the attraction between the liquid and the container that it's in. And then cohesive forces are just the intermolecular forces of the liquid itself. all right? And so this sort of balance between adhesive and cohesive forces is going to determine some of the properties of a liquid when it's in a glass container or any type of container. So what you can have then is, for different liquids, is you can get what's called a convex or a concave meniscus. So you guys, if you've done stuff in the chem lab where you had to read the volume of a liquid in a graduated cylinder or a burette, you notice that the surface of the liquid is not flat in most cases. It's curved a little bit. Usually for water, it's going to be curved in the concave direction like this, but other liquids might be curved convex. And so the reason that you get these different types of meniscuses at the surface is because of the balancing act or the competition between the adhesive and the cohesive forces. So if you have a nonpolar liquid, the cohesive forces are stronger, meaning that the liquid's forces with itself are stronger than their attraction to the container. So the cohesive forces are greater than the adhesive forces. I did not do a good job of that. I must have moved this graphic out of the barely room there. Okay, so cohesive forces are stronger than the adhesive forces when you have a convex meniscus. And that's because, again, the molecules are pulled more strongly towards each other, so they're kind of bunching up and getting pulled downward from the surface of the glass. But then the opposite case, when you have polar liquids like water and you put it in a glass, in that case we said the surface of the glass is polar, the water itself is polar, so you have pretty strong interactions between the water and the glass. And so the water will sort of start climbing up the sides of the glass. You'll start having these greater areas of contact, and that'll result in a concave meniscus, where the adhesive forces are now stronger than the cohesive forces. So that's one of the consequences of these adhesive and cohesive forces, is that you can get meniscuses that are either curved upwards or downwards, depending on which one of those is stronger. So polar liquids tend to climb up the side of the glass because they have strong forces of attraction with the glass. Nonpolar substances tend to sort of shrink away from the glass and sort of kind of bunch in with themselves because they have very weak interactions with the surface of the glass, and that results in these different behaviors. So those are some other properties of liquids that depend on intermolecular forces, and then we'll talk about one last one here, which is viscosity. So viscosity's technical definition is it's the resistance to flow for a liquid. But in simpler terms, it's a measure of how thick the liquid is. And again, it's directly related to intermolecular forces. The stronger the intermolecular forces in the liquid, the higher its viscosity will tend to be. All right, so if you have a liquid like water, I think this one on the left is probably just water with food coloring in it, but I'm not sure. But you know that water actually flows pretty easily. If you tip over a beaker of water like this, it's going to pour straight out. It flows very readily. That means this one has relatively low viscosity when it flows very fast like that. But then if you had a beaker with like a motor oil or a motor oil additive in it, if you turn that over, the liquid would pour very slowly. That's when you have high viscosity. So it's how thick a liquid is or how fast it would pour out of a container. And so this is going to be a high viscosity liquid here on the right. All right, so that's what we mean by viscosity. It's how thick the liquid is, how readily it pours out when you tip it over. And again, the stronger the intermolecular forces, the higher the viscosity will tend to be. So if we look at these substances here, let's predict which liquid has the highest viscosity. And so what we have in this situation are, three substances. They're all very similar in their size. So, the size of the molecule does matter because that's going to dictate the London dispersion forces. But these are all similar in size, and so we have to figure out then which types of intermolecular forces do we have to be able to predict which one has the highest viscosity. So if we look at this compound here, the first one is what's called a hydrocarbon. It's just carbon and hydrogen in a long chain. And without even having to draw it out in detail or think about the shapes of the molecules and the polarity and all that stuff, a very useful thing to remember, both for this course and if you take organic chemistry in the future, is that hydrocarbons, compounds that just have carbon and hydrogen in them, are always going to be nonpolar. All right, so it's not obvious necessarily from the structure, but basically what you have is all the carbon atoms are tetrahedral, so all the CH bond dipoles, which are very small to begin with, cancel each other out anyway. So in a hydrocarbon substance, only carbon and hydrogen in the formula, you're going to have nonpolar substances. So this is going to have only London dispersion forces as the intermolecular forces present. And that's going to be true for any hydrocarbon substance. All right, and then the next one here is, again, similar in size, still a chain of 5 atoms with some hydrogen in it, but now we have oxygen in the center here. So when we put oxygen in the center here, we need to again think about the shape of the molecule a little bit. And in this case, oxygen has 2 lone pairs on it, which aren't shown here. But what you'll get then is a bent sort of geometry. So you'll still have these sort of flexible hydrocarbon chains at the end, but you're going to have an oxygen in the center that's bent. 2 lone pairs makes it bent, and then we're going to have, again, dipole moments pointing towards oxygen. So when you put one oxygen in the center, you now have polar CO bonds, and because it's a bent molecule, those bond dipoles don't cancel out. So this is going to be a polar molecule, and it's going to have dipole-dipole forces. So we'd expect the intermolecular forces to be stronger in this molecule and for this to be a little bit more viscous. In reality, these 2 substances are similar in terms of viscosity, but this one's probably a little bit higher viscosity. Then if we go to the last one here, this one has now 2 oxygen atoms at the end with OH bonds present as well. So whenever we see a bond between hydrogen and oxygen, that should cue us in immediately that this substance here it's also polar. But because of the OH bonds, it has hydrogen bonding interactions, which make it the strongest intermolecular force. So basically, these 3 substances have 3 different types of intermolecular forces as their strongest. So this one, the strongest force is London dispersion. The center one, the strongest force is dipole-dipole. Here, hydrogen bonding is the strongest intermolecular force, and this is the strongest type, so this one would have the highest viscosity. So again, whichever one has stronger intermolecular forces is going to have highest viscosity, and this is called propylene glycol, and this is sort of like an antifreeze type substance. I don't know if it's the exact one they use, but you know those antifreeze substances typically are very thick, and when you pour them, they pour out very slowly. So when you have these hydrogen bonding interactions, you're going to increase the thickness or the viscosity of the liquid, and that's what we would see for this one here. All right, so any questions on those properties of liquids? We're not going to, again, go into a lot of deep depth with most of this stuff. That's as much detail as we're going to get on the properties of liquids. So if you have any questions, let me know, and I can handle those now, or we can move on to the next topic. All right, so that's kind of, and then the last property we're going to talk about with liquid is called vapor pressure. Now we introduced vapor pressure in chapter 8, I guess last chapter, pretty recently, in the context of those problems where you collect a gas over water and the total pressure is equal to the gas pressure plus the vapor pressure. So we kind of know what it is when you talk about it in a little bit more detail in this chapter, and that'll help make the last chapter make a little bit more sense, hopefully. All right, so first we have to, again, talk about vaporization, which, as we said, is sort of used interchangeably with boiling. But vaporization is typically a process that happens spontaneously, whereas boiling is a process that requires you to heat the substance up, so that's a little bit of a difference in terms of how they're used. But it really is just the process of converting a liquid into a gas. All right, so that's what we call vaporization. And then vaporization has an enthalpy change associated with it. So all of these phase changes now, we haven't talked about them in great detail until yet, but all the phase changes have an enthalpy change associated with them. How much enthalpy is required to change the phase of 1 mole of that substance? So for vaporization, we call it the vaporization enthalpy, not too surprisingly, abbreviated as delta H VAP. And this is the enthalpy change associated with vaporizing 1 mole of a substance. So if we want to convert 1 mole of a substance from liquid to gas phase, the enthalpy change associated with that is called the enthalpy of vaporization. So even though it's a physical process, it's not a chemical change, it still can have an enthalpy change associated with it, and that's going to be called the enthalpy of vaporization. And vaporization enthalpies are always endothermic. meaning the value for delta H vaporization is always positive. And that should again make sense because if we're vaporizing something, we have a liquid which has intermolecular forces holding the molecules together. If we want to vaporize it, we have to break those forces so that the molecules can completely separate from each other and become a gas. And so you have to put energy into the system, heat into the system in order for that to occur. You're breaking forces that are holding things together. Okay? And then condensation is the reverse process, as we talked about earlier. And this is when molecules in the gas phase become a liquid, so change back to liquid phase. And so this will have a phase change enthalpy associated with it as well, the delta H of condensation, but we should recognize that vaporization and condensation are exactly opposite processes. As we talked about in chapter 7, when you reverse the direction of a reaction or a process, you just reverse the sign of delta H. So the delta H of condensation is just the negative of the delta H of vaporization. So there's really only one value that defines those two processes. It's just whether it's positive or negative. Positive for vaporization, negative for condensation, but the value is the same because it's the exact reverse process. All right, so that's kind of some things about, that relate to vapor pressure, because vapor pressure, again, deals with the idea that some molecules in a liquid are going to be vaporized, they're going to be above the surface, and they're going to be exerting a pressure. So let's then talk about then what causes this vapor pressure to occur. So we're going to place a liquid in a closed container here. So we have a liquid in a closed container. So at the very beginning, if all the molecules initially are in the liquid phase, at the very beginning there's going to be net vaporization occurring. Not all of the molecules are going to vaporize unless it's a liquid that exists as a gas at those conditions, but at the beginning there's going to be some vaporization, net vaporization, because some of the molecules on the surface are going to escape into the gas phase. All right, so here we're showing again the beginning situation. So at the beginning we put the liquid in the container, and if we assume at the beginning that all the molecules are in the liquid phase, some molecules at the surface are going to have enough energy to escape into the gas phase. All right, so not all of them, but some molecules have enough energy, they escape into the gas phase. So at the beginning you have net vaporization, but then eventually a constant vapor pressure is established because you're going to have essentially equal rates of vaporization and condensation. So we abbreviate vapor pressure as PVAP, pressure of the vapor, and eventually you're going to get to a constant vapor pressure. So at this beginning part, as the molecules start escaping into the gas phase, the vapor pressure is going to increase, but eventually it's going to get to a constant value. And that's because as you get to what's called equilibrium, the situation where you've gotten to that constant value, you'll have your liquid, and you'll have some molecules sort of escaping the surface of the liquid, but you'll also have molecules that condense back into the liquid from the gas phase. So you kind of have this back and forth process. Some of the molecules are going to be escaping, but some of them are going to be coming back. And eventually you get to the situation where the rates of those two processes are the same and they kind of balance each other out, and so your vapor pressure stays constant. So you'll have some molecules in the gas phase floating around that cause a vapor pressure, but at the same time you're going to have new molecules escaping the surface, but other molecules going back, and it kind of balances itself out eventually, and you get to a constant vapor pressure value. All right, so what this looks like sort of in a graphical sense is we're going to show here, this is sort of the rate at which these processes are happening as a function of time in a liquid. So we're going to talk about vaporization in blue. And that is going to be a constant rate of vaporization. So at a constant temperature, the rate of vaporization is going to stay the same. So your vaporization rate is going to be flat as a function of time. But then in red here, I'm going to show the condensation rate, which is the rate at which molecules condense back into the into the liquid, and this one is going to initially increase before getting to a constant value. And the reason for this is because at the beginning you don't have any molecules in the gas phase. You can't have any molecules condensing back into liquid if there's none in the gas phase to begin with. But as more molecules go into the gas phase, some of them are going to start condensing back. And again, you eventually get to a situation where the rates of vaporization and condensation become the same. So again, vaporization in blue, condensation in red. And at some point you get to a situation where those two rates are constant, and that means the vapor pressure gets to a constant stable value. So the whole point of all of this is that when you put a liquid into a closed container, you're going to have a vapor pressure, but the vapor pressure doesn't continually increase. It increases initially, and then it gets to a stable, constant value, and that's because those two opposite processes happen at the same rate as each other, and so it kind of balances itself out. So that's going to be how it works for vapor pressure, sort of why it happens. And to talk about it then in a little bit more detail, let's talk about how to measure vapor pressure with a barometer. Again, this is just mostly for background of how do we get these values, because every liquid is going to have a measured vapor pressure. How do we determine what that value is? So the way that you do this is you first measure the atmospheric pressure with a barometer. Because we talked about in chapter 8, the vapor pressure of water is 24 torr at this temperature or whatever. So how do we get that value? Where does that come from? So one way to do it is to use a barometer. So you measure the atmospheric pressure with a barometer, and then you're going to inject a liquid into the top part of the barometer. So this is like a really crude way of measuring vapor pressure, but it does work. So what you initially do is you measure just the atmospheric pressure. So a barometer, again, is like a dish of mercury with an inverted tube, and then the mercury rises up the tube. Let's make it go a little bit higher than that. So the mercury rises up the tube because it has atmospheric pressure pushing down on it. And that forces the liquid up into the tube. And initially, in the top part here, above where the mercury rises to, you have a vacuum. So initially, there's no pressure up here. It's just being opposed by vacuum. And so that forces the liquid up the tube. And again, this is going to be around 760 millimeters of mercury if you're at sea level. So that's what happens initially. You measure the atmospheric pressure that way and get the initial height of the column. And then what you're going to do is you're going to add a liquid to this top empty part here what's initially under vacuum. So you add a liquid to the top, and then what you have is sort of two forces opposing each other. So I'm going to draw this in kind of an exaggerated way, but what happens is you have your dish of liquid mercury, then your barometer that's in there. But what you have now is a liquid above the surface. So what happens is you have your atmospheric pressure pushing down that way, and then you have your vapor pressure from the liquid pushes down in the opposite direction and forces the level of the mercury to be decreased because of the vapor pressure pushing back down, opposing the atmospheric pressure. All right? So as an example then of how you get this numerically, if we assume the atmospheric pressure is 760 millimeters of mercury, then the height of this column here, which once you've added the vapor, is going to be equal to the difference between those two, the atmospheric minus the vapor pressure. All right, and we're going to reduce the height of this column by the amount of vapor pressure that we have pushing down on it. So if you have water at 25 degrees Celsius, we would measure the height of the column as 736 millimeters. So once we inject a little bit of water in the top here, the column goes from 760 and it drops a little bit because of the vapor pressure down to 736. And that means the vapor pressure of water at this temperature is 760 millimeters minus the new height, which is 736, which is 24 millimeters of mercury.
What
the vapor, VAP. All right, so that's how we measure vapor pressure, just a little bit of background on that. Just to cue you on how you would do that experimentally. Again, not a terribly important thing, but just to show you how it's done. But the more important thing we're going to talk about is how does vapor pressure depend on two things in a liquid. So the first one we'll get to today is temperature of the liquid, and that we should be able to close up with that, I think, if we have time. And then also how does it depend on the intermolecular forces in the liquid. So first we're going to talk about how temperature affects vapor pressure. So what we're going to do here is sort of plot, kind of like we did, remember we talked about the distribution of speed for, for gas molecules. So in a gas you have a average molecular speed that's determined by the temperature, and you have a distribution of values across a wide range. And the same thing sort of happens in a liquid as well. So it's not the exact same relationship, but conceptually it's the same. So if you have a sample of a liquid, the molecules in the liquid are going to have a distribution of kinetic energy values. So at some initial temperature, which we'll say is our colder temperature, so at our colder temperature, we'll have some distribution of kinetic energies in our liquid. And as we said in the sort of pictorial description of vapor pressure, some fraction of molecules are going to have enough kinetic energy to escape the surface of the liquid. They have to escape those intermolecular forces that are holding the surface of the liquid together. And so some small fraction of molecules can escape the liquid. So at a low temperature, it's just going to be a pretty small percentage of molecules that escape the surface that would have enough kinetic energy to do that. So let's say that this is the amount of kinetic energy necessary to escape the surface, so only this portion of the molecules would have enough kinetic energy to escape. So that's the situation when we have a lower temperature. Now let's say we heat up the liquid to a higher temperature, so we'll call T2 our higher temperature, same axes, fraction of molecules, and the kinetic energy that they have. But just like occurs in a gas, when we heat up a liquid, we're going to have a wider range of kinetic energy values, but they're going to shift towards a larger average value. So when we heat up a liquid, the kinetic energy on average increases as well. So our distribution is going to shift to the right and be a little bit broader. And so now we're going to have, let's say, if this is the kinetic energy that's required, a much larger fraction of molecules have enough kinetic energy to escape the surface of the liquid. So as we increase the temperature, more molecules have enough kinetic energy to escape, and that means more of those molecules will go into the gas phase and we'll get a higher vapor pressure. So when you increase the temperature, you broaden the distribution of kinetic energies and you shift it towards higher values on average, and now more of your molecules will have enough kinetic energy to be able to escape the surface of the liquid. So the net result of all of this is that the vapor pressure increases as the temperature increases. So qualitatively speaking, that's what we would say. Vapor pressure increases as the temperature increases. And there is an equation for this that we're going to talk about a little bit. And I think we'll have at least some homework problems on it, but it's not, again, going to be a major focus. But there is an equation that describes this. So the conceptual part is that increasing temperature increases vapor pressure. And so the equation here is that the natural log of the vapor pressure, so this is the first equation we have that uses logs in the formula for this course anyway, so make sure that you're familiar with how to do natural logs or logs of any type. And this is equal to the negative of the vaporization enthalpy divided by R, where R is the universal gas constant, times 1 over the temperature, plus a constant C. Now this constant C, though, is not universal. It depends on what substance we're talking about. So this is not a particularly useful equation when written like this, because we have a constant here, C, that depends on what substance we have. It's not going to be well defined for all substances, and so this form of the equation is not used all that often. The form of the equation that is more useful is what we're going to take for a single substance, and we're going to compare two different vapor pressures at two different temperatures. And so then what you get is a useful form of the equation that looks like this, where we don't need this constant anymore. So the natural log of the ratio of the two vapor pressures, P1 over P2, is equal to the enthalpy of vaporization divided by R times 1 over T2 minus 1 over T1. There's actually two forms of the equation. You could have left the negative sign out in front of delta H vaporization and then flipped T1 and T2 under this parentheses. So you might see that form of the equation in other places. Mathematically, it's the same, and this gives you a relationship between two vapor pressures, P1 and P2, at two respective temperatures, T1 and T2. And that way we don't need this constant C in the equation. It's just a comparison of those two, where all we need is the vaporization enthalpy for that substance, which is well defined for a lot of things. So the important parts are the temperature need to be in Kelvin, and we're going to use this value of R, which we haven't really seen yet, 8.314. We talked about it a little bit in the context of molecular speeds for gases, but anytime we're dealing with energies, speeds, things like that, we need to use this value of R, which is in joules, because our vaporization enthalpy is going to be in joules as well. So there's a linear relationship here between the two then. So if we take the natural log of the vapor pressure and plot it as 1 over the temperature, so on the y-axis we're going to put natural log of vapor pressure. So the other reason that this equation is useful is that it gives you a linear relationship, where if we measure vapor pressure as a function of temperature and plot it in this way, the slope of this plot from this equation up here is equal to the negative delta H over R, and the intercept is that constant C. But this also gives us then a way of measuring the enthalpy of vaporization. We just measure vapor pressure at different temperatures, and the slope then is related to the enthalpy of vaporization.
What does that say, like slope equals what?
Delta H over R, and particularly the vaporization enthalpy over R.
Delta H over R.
Yes, so delta H is the vaporization enthalpy in this case. So that's the slope of this plot. So if we have water, for example, you would get a plot that looks like this with a pretty steep slope because it has a high vaporization enthalpy. But then if we go to something like, what's a good example for this? If we go to something like methane CH4, which is actually a gas at room temperature, it's going to have a much smaller enthalpy of vaporization because it doesn't have hydrogen bonds, and so the slope of this one would be much more shallow. All right, so different substances would have different slopes, and that allows you to measure the vaporization enthalpy. So the other reason that this equation is useful is because it's a way of measuring delta H of vaporization. But the form that we're going to use primarily is going to be this one here. And so we'll close out with one quick example problem on that. I'm running out of time, but I want to make sure I just get to this since it's closely related. So if we have this substance diethyl ether, it has a vaporization enthalpy of 21.9 kilojoules and a vapor pressure of 0.703 atmospheres at 25 Celsius, what is its vapor pressure at 95? Now conceptually we know that if we raise the temperature, the vapor pressure should get much higher than this. So let's see what it comes out to numerically. So again, this is the equation. P1 over P2 is equal to delta H of vaporization over R times 1 over T2 minus 1 over T1. So T1 is the initial temperature that we're talking about, which is 298 Kelvin. These have to be in Kelvin. P1 is the initial vapor pressure at that temperature, which is 0.703 atmospheres. Because it's a ratio, the pressure units can be whatever you want them to be. And then T2, which is the temperature we're trying to find, is 95 Celsius, which is 368 Kelvin. So those are the numbers we have to put in along with delta H of vaporization. So the natural log of P1, which is 0.703 atmospheres, divided by P2, which is what we're solving for, is equal to the enthalpy of vaporization. That has to be converted to joules, 21,900 joules per mole, divided by R, which is 8.314. And the reason that needs to be in joules is because that's what R is in terms of in this form. And then 1 over T2 minus 1 over T1. So 1 minus 368. 1 1 over 368 minus 1 over 298. Those are the two temperatures in that order if we're using this form of the equation. And so numerically, we just work out this whole right side of the equation. It comes out to minus 2.234. And so then if we want to do, we have to learn the algebra a little bit here. So if we want to get rid of the ln, we take e to the power of both sides. So we get rid of the natural log, it's going to be 0.703 atmospheres divided by P2 is equal e to this power. So again, we use e to that power to get rid of the natural log on the other side. And then numerically that's 0.107. So then solving for P2, we get 6.56 atmospheres. So we predicted that the vapor pressure would go up a lot when we raise the temperature, and in fact it is quite a big increase from 0.7 to 6.56 atmospheres. So this is how it works out numerically. It's just one equation that relates vapor pressure and temperature, so make sure you understand how to use that. Any last quick questions before I wrap up? All right, so next time we're going to talk about more properties of liquids and a little more detail about phase changes that involve all liquids, solids, and gases. So we'll see that on Thursday.